processing method, and basically all she says with that is you can modify the loss function to achieve fairness goals. So her simple example, like a naive example, would be that if the answer is not fair, you like increase the loss function by 1. Obviously that's not very good because your model will never, like, highly unlikely your model is perfectly fair, but it's, you basically just modify the loss function to depend a bit on some fairness constraint. And the other thing you can do is model selection. She adds that as a sentence. I don't know.
Add more layers?
So is this for
Just for in processing. So it's
bias
how,
in the process?
we're past
We're past
we're
that.
past bias. This is like trying to make your model or your predictions fair.
Okay.
So with in processing, you can change your loss function to penalize it if it's not fair.
Okay.
So are all these methods trying to get us to approach like one of the fairness
Yes.
metrics?
Yeah, and which fairness metric you want depends on your situation.
Sure.
Yeah. And then for post-processing, we have the equalized odds algorithm, and it's the dumbest shit.
Great.
Basically, the equalized odds algorithm says if it's not equal, you can flip coins until it is equal. So
Equalized
if we
odds
have
algorithm.
A, and they have been all accepted, or let's say like 80% of them have been accepted, and you have group B, and the model predicts that only 2 of them should be accepted.
Not equal.
This is not equal, yeah. We don't have demographic parity here because here we have 80% accepted, here we have got 40%. What the equalized odds algorithm seems to say, it's ridiculous, is, well, some of these people we can just kind of flip coins until we get demographic parity. So we might say, oh, this one is a 1, and this one is a 1, and now it's fair.
So we just edit
That doesn't
the
make
results
any sense.
Yes.
without even touching anything. So a
Yeah.
model gives us one thing and it's like
Yeah, pretty much, yeah. And the reason why you would have to do this, it's a last resort. Post-processing is your last resort. You would do it if you don't have access to the model or the data, like you can't change that. You were just given a bunch of predictions, and you're like, shit, I've been given this bunch of predictions, I have no access to the model, I have no idea what data it was trained on, I know none of this. The only thing I know is what the results are. I can just let some extra people in so that it meets my demographic parity that I want.
So this is like, so there's different things to make your model fair at different stages of the pipeline, and
Yes.
this is the last stage of the pipeline, and this is
Absolute last resort.
absolute last resort. What
Because-
about like
because it's just random.
adding like
You're
a
literally just saying
threshold
these
or
2 guys should be accepted so that it's the same number of people accepted.
So we just fuck up our whole entire model just to make it fair.
Yes.
Welcome to the course, bro.
that doesn't sound ethical at all, yeah.
So-
That sounds super unethical.
So, Elijah,
Yeah.
what I assume is if your model sucks, it has to suck for everybody.
Yeah.
Or it has to suck.
Well, the model might be great. It's just you don't know what the model is. You weren't given that. You were just given the predictions. So like if you were literally just given a list of people and it says yes you're allowed in, no you're not allowed in, with no other information, how would you change that to let people in? You don't know anything about these people. You just know whether they were accepted or not. Flip a coin.
So if you flip a coin, like let's say I get 0, do I put a 0 or do I just keep flipping until I get 1?
I guess you just keep flipping until it's the same.
So I just,
Honestly, I think it even might be like, I think you might even be able to do something like, look, you're actually not allowed in anymore. Like, I think it's literally just flip until you get equal.
So this would be related to, like, if your boss says like these have to be equal, then like
Yes.
you're
And
making it equal.
Exactly. Your boss says these have to be equal. The government. The government says
Hard code.
you need to accept equal amounts of people.
Stupid fucking
Yeah.
And you're given a list of people. If they're not equal, you just kind of
All right.
make
cool.
it equal.
All right. Cool.
Yeah, I mean, you guys can like double check the slide. It's like the end of chapter 3, but that's what
I'm
I
not
see.
gonna double check it.
Yeah. Yeah. Okay. Chapter 4. So now we're going to try to remove protected attributes. So that would be information about the groups. You want to get rid of that. The first thing you can do is regularization. So
What's this again?
this is just the beginning of chapter 4. So the idea for this chapter is how do you remove protected attributes,
Okay.
like race or gender.
6.
If you have like earlier I said, like we have like our whole bunch of features that are all like this, right? This idea again. If you have a whole bunch of these and they are weakly correlated with the actual group, what you can do is you can apply regularization, and regularization will try to remove these weak correlations.
Sorry, can you explain what that graph is?
Yeah. If you've got a whole bunch of features, right? This is like feature 1 and this is feature 2, and it is distributed within the populations as like group A, group B, group B, group A. Since these distributions are different, given if you have enough of these different distributions, you will be able to tell from the combination of them whether a person came from group A or group B, because your first data point might be here, just a little bit to the left. Let's make it so it's like more clearly inside. Yeah. So it's a little bit to the left, and over here, it's like a little bit to the right. Over time, as you get a whole bunch of these, like this is very likely. But if you have like 100 of these, where it's always being like, it's straight in the middle of A, but it's like really off to the side of where most of B is, you can figure out what the group is without actually having the group.
Yeah.
Regularization will remove this ability to predict it because it tries to limit the effect of weak features or weak feature combinations. So this is like, even though it is slightly more likely to be A here, regularization will say, we don't care about things that are very small like that, and it will remove it.
Makes sense.
So what would it do to these graphs here?
It doesn't do anything to the graphs, it just it affects the weights within the model.
Okay, gotcha.
Yeah, so the first thing is, I mean, she starts off with the lecture with this, but it's the same thing as mentioned before. If you remove all the dependents, right, so all of those things, they look the same, you get demographic parity because you can't tell the groups
So
apart.
this is a type of regularization?
We're going to get into how you remove them,
Okay.
just accept that you can. But, yeah, so the first thing you can do, the first thing is in-processing. Again, I forgot, the learning fair representations is in chapter 4, but it makes more sense to talk about it in chapter 3. So if you remember everything I said about doing the prototypes, that's the first way you can remove the dependents, right? Because you're mapping all of them. And I guess that's a way that makes sense, right? Because if originally you had your X's and your O's all being mapped to like some box like here, and remember, like you have a lot more features, right? So it's not like this is pointless, but if you have enough things, when you map them, you'll be able to still learn something from that. Since they've all been mapped to the same area, we've gone from having this to just having one. So that is the first method of in-processing to remove the correlation between features and the groups. So that would be your pre-processing way to do that, because you do that on the, I meant to write pre-processing in my notes, that's why. But yeah, so that would be like, because it's before you actually give it to the model. For in-processing, we have adversarial debiasing. So adversarial debiasing is very similar to like the generative adversarial networks we learned about in some course that we all took. Yes, Yemen. And the idea is we have our main model, and it is trying to predict like the target, right? It makes predictions, but then you feed the information that it predicts into an adversary, which is trying to predict, so this is like your main model, and this is your adversary. And it is trying to predict what group this certain person is based off what it predicted. If it gets it right, like, so that feeds back into that. If it gets it right, then it adjusts, the model has to adjust so it doesn't predict in a manner to where the adversary can predict what the original group is. So all you're trying to do is train a model that can predict the actual value without giving away information about which group that it came from.
So the adversary just predicts the group?
Yeah, the adversary is trying to predict what group somebody came from, and the model is trying to predict the right value while also not telling the adversary which group they came from. So the adversary's loss function would just be like, I don't know, like sigmoid or something. Like it's like one of the classification ones, right? It's trying to like, or it's like finite cost function or whatever. It's like, because it's trying to classify a group, but then your normal model's loss function would be the, like whatever your model's loss is, right? Plus some weighted amount of whether or not the adversary got it right. So what you're trying to do is just limit your loss while not letting the adversary predict it right. So if you remember from the lab that we did, when you added the adversary, you like your loss or your accuracy decreased, right? A little bit, like just like a tiny little bit, but also the adversary didn't really like get worse over time, and that was because the information from your prediction was almost entirely enough to already predict the group. So the adversary like won, I guess, like, but in other cases, like your model would eventually be able to beat the adversary. It might take like a 10% hit on accuracy, but it would be able to hide which prediction it came
So
from.
both these methods are trying to like reduce correlation between features and the group?
Yeah, yeah. So this is just your model's trying to predict in a manner in which you can't predict the group from it using an adversary.
Okay.
Yeah, I feel like that makes
And the
sense.
goal is to make the adversary not guess the group correct.
Yes. And you can use this for different fairness metrics depending on what inputs you give to the to the model. So like you can use it to equalize the odds, you can use it to get demographic parity. It just all depends on what you actually give the adversary. She doesn't say what you can give the adversary, so yeah.
What is the model? The model is giving us a prediction.
Yeah, the model is just like the normal model we've been talking about the whole night. It's just whatever model you're using to predict, and it's competing against somebody who's trying to predict the group based off what the model initially predicted.
Oh, okay.
So does the adversary only get the output of the model, or
That's what I don't know. She doesn't say what inputs the adversary actually gets. She draws a diagram of it getting Y, but it must get more than just Y.
right?
So I'm not sure exactly what the adversary gets, but
Okay.
yeah. And then post-processing is the easiest one this time. For post-processing, they just talk about changing the threshold. So if you are given a model that instead of just getting our like plain predictions of ones and zeros, instead we get probability of defaulting, right? Like 0.7, 0.7 from like group A, and then group B, say it's like 0.55 and 0.3. You might adjust thresholds for certain groups to let in more people. So if originally you're like, we're only going to let in people if they get higher than, we'll make this less than 0.5. Because normally it's like more than 0.5, you're saying it's good. You can adjust the threshold lower so that now you're accepting people from other groups. And the reason why you would do that is because if the penalty of a certain thing, either one way or the other, is extremely high, you will want to change your threshold to be closer to like not having like the devastating outcome, I guess. Like if it's trying to predict whether or not you have a disease, and the disease is really bad if you get it, you wouldn't want the model to be like at least 50% confident to get further screening if you were just doing like a cheap at-home test. You might instead like set the thing being like, if you even have a 20% chance of having cancer from like a home test, you should go in and get properly screened. So that's what thresholding is, and that's something that you can do with post-processing.
How does that have anything to do with like correlation between features?
Yeah, I don't know, man. It's in that section. It probably
Read the
says in the
slides,
slides.
bro.
It's probably like last ditch effort, no, right? Like once again.
Yeah.
It's after everything.
Yeah, post-processing always is the last
So
thing
if
you
you
want
can
to
change
do.
your threshold for like a group that's unprotected or whatever, then you could technically make it harder to tell between groups if your threshold's different, right?
Yeah.
That's,
Yeah. So then the last thing, I think this is relatively important, is the Shap or Shapley value. In the slides, she calls it the Shap value, like this. And then in the questions, she calls it Shapley, like this. So look out for that. I don't know why she changes what it's called. I haven't even seen this anywhere else, so I don't know if that's I think, but she has written it both ways. And what the Shapley value is, or the Shap value is, it's basically a measure of how much a given feature contributes to the final prediction. And the way that you would obtain that is you look at every different permutation of features together and try to predict off them, and you see how that impacts your final prediction. So if you're trying to predict house prices, and you've got three things, you've got like the area of the house, which is this box. You've got whether or not they can have cats, which is this triangle, and you've got whether or not it's near a park. The Shapley value will essentially, it will check all the different combinations we're trying to predict, or well, I don't know if it's trying to predict so much as it just knows the actual value, and it will see how they're correlated. So if you take like just this, it might say that the house is worth like $300,000. Versus if it takes like this and this together, it might say that this is like $310,000. And yeah, this maybe it says it's like $315,000. So basically from that, you learn the relative importance of the different features. So you know that the square footage of the house is very important to its value. Being near a park is kind of important to its value, and some third thing is like not very important towards its value. And from that, like this is important for model interpretability. It's like this is all just used for feature selection. And it's important for like model interpretability because you now have an idea of how important each feature actually is going forwards. So you know if something has some kind of issue with it and it's got a high like importance, that's problematic. But also you know if something is only represented in the less common group and it's given a low importance, like that could also be an issue because it shows that your model is not treating that as very important because it's not important for the main group. Sorry, that's a poor explanation. What happened? Like really, like there's a couple properties of the Shap value that is valued. So the first one's the interpretability, which is just saying if it's got a higher Shap value, it's more important to the prediction. The other thing is the null property. If it's not important, it'll be given a value of 0. Then there's also like, it's like additivity or linearity or something like that, which is saying if you use two different models in a row to combine it, if you add up the Shapley values from each one together, then you know how important it is overall. What are the other two?
Equality.
Laura?
Equality, not one.
Yeah, I think it is, yeah.
It's like two features that have the same like.
Yes, yeah.
job,
Yeah, so equality is another one. If like two features are equally important to the model, have the same Shap value. And then there's also one that's saying if you change the model, so maybe you go from just like a linear model to a neural network, and some feature becomes more important, then the Shap value will also increase, obviously. But it's an important feature because apparently some things maybe it decreases, and that would be bad. But it's basically all it is you're looking at the marginal effect of a variable. That's the main takeaway.
Do you know how to like, get those values?
No, it's just done by an algorithm. Because it computes all the different permutations of like feature 1 and feature 2 together, just feature 1 alone, all the features together, and it sees how that changes the answer, and that's how it determines how important each feature is. Okay.
Based on these Shapley values, like, should we make changes to our model?
Well, I mean, like you use it for feature selection because from that you can see how important different features are.
So if it's 0, just get rid of it. Okay.
For like the Shapley value, you can have like positive and negative numbers that's like based off like a ground truth. But what is like the ground like truth in this case?
Like the absolute magnitude is just how important it is, I think. Or Laura, do you have the slides open?
I have it right here. So
'Cause-
magnitude,
yeah.
larger just means bigger impact. That's pretty intuitive. And then the sign, this says positive pushes prediction higher than baseline and negative pushes lower. So like if the Shap value is like -6, then that means
Oh, yeah.
that feature is strongly pushing it lower than the
Yeah, so you'd have like another feature, and this is you live beside the ghetto, so that would push property value down.
What in this case would be the baseline?
Yeah.
Baseline would just, I guess it would probably be the average across all of them. I don't know exactly. I don't think it says.
I don't see it.
The baseline is probably like
It's the baseline, bro.
just the average. Like I would assume it's probably something like the average house price, and then like bigger houses will increase value.
Bring it up with
You know.
whatever her fucking name is, bro. Don't ask me.
Sorry. Okay.
I need to hear this.
Chapter 5.
When did it start?
So decisions are made using utility, and utility is different for each person. For example, if I want outcome, like outcome 1 might be more valuable to me than outcome 2. So based off the utility of the different outcomes to me personally, and that's another thing. Utility is hard for like interpretability and stuff because it's different depending on the person.
It's like preference.
Yeah, it's just preference. This is ground week 5.
Wait, this is week 5?
Yeah.
Utility?
Yeah. Utility and decisions is the main ideas for week 5.
We have 7.
No. So yeah, but yeah, utility is just how valuable something is to you. You want to value different outcomes against each other. And the reason why it's important is because you can have a model that just makes predictions, and predictions are different from decisions because a prediction is just how likely a certain outcome is to happen, whereas a decision is given the different likelihoods of different outcomes happening and how much I value them, I then have to choose what I would prefer to do knowing that. Like it's like the easy example would just be like, would you rather have guaranteed chance at $1 or 50% chance at $10? You'd probably gamble because you're more likely to have more, like I would value a 50% chance at $10 more than 100% chance at $1. There's higher utility for that second choice. And for when you're making decisions and you're trying to weigh these different things, there's the idea of like a Pareto or Pareto dominated thing. So that's like if for 2 people, the utility of one option is like 0.5 and 0.5, and there is some other option where nobody is worse off, so like this guy's still 0.5, and this guy now has a utility at 0.6, this is always the better option. It's always better to, if there's an option that increases utility for everybody, or at least maintains their current utility, that's the better option.
So it's just like the idea of like preference, but mathematically preference.
Yeah. So going off of that, we can, yeah,
Oh yeah, what's the proper term for that example you did?
Pareto dominated or something? Pareto? I don't know.
What does that term mean?
It just means that if there's an option where nobody is worse off but somebody is better off, that is the better option.
Okay.
It's like win-win, you know, no, or at least win and nobody loses.
Right.
So when we're making decisions, you have like a policy, which is represented with like pi, I think. Yeah.
Yeah.
So the decision is given all of the probabilities of different outcomes. So if you know that if you're trying to give a loan, you might have to make this decision based off the likelihood of default versus not default. And then the way you try to make that decision is also by weighing the utility of if you get the loan and it works out, you make like $1,000. If you get the loan and default, you lose the money plus the opportunity cost. Maybe that's like negative 2,500. So then based off the likelihood of default and knowing your utility, you are able to make a decision. And you can train models to make decisions by just trial and error, pretty much, is one way. But
Sorry, what was that equation with the pi you put there?
it's just a pi. So it's just a policy. A policy is how you choose to make decisions.
Okay.
Like a policy could literally be as simple as like, we will give you a loan if there's a 50% chance you pay it back. Like that could be a policy that somebody could have. And the way you make decisions is like, so one way to make decisions is just to have your policy and you just stick to it. Yeah.
This is outside the model, right?
Yeah.
Okay.
Yeah. Like she has a diagram where it's showing it, a way you can implement it in the model, but it's just a diagram, so I don't know. So what you can do though over time is your initial policy might not be the best way to think about it. So what you might have to do is, and there's no way to learn, okay, let me just, get an example. I feel like that's easier. I don't know what I'll say. If you've got a group of people and your model says, like, here's person 1, they got 0.7, 0.7, 0.3. And you have some policy that says we loan to people who've got scores of at least 0.5 based off how our model works. That's great. You take these two people, maybe one of them pays and one of them doesn't pay back. Yeah?
What's the difference between a policy and a threshold?
They're pretty similar.
Okay.
Yeah.
So that a policy can be based on a threshold? Is that true?
Yeah. Yeah, like the way she has policy notated is like a decision is based off the likelihood of a bunch of different things, the likelihood of all the different outcomes, and also like a decision can also always be like to do nothing kind of thing, so you have to consider that decision as well, and the opportunity costs associated with that. But basically, if I have this thing and I decide to loan to these two people, and one of them pays back and one of them doesn't pay back. That's good. Like, let's say I made money off that, and that's fine. But the issue is you aren't improving your policy over time. Like, you can improve your policy over time by adding randomization. And the reason why you would do that is because, sure, your model is saying that this person had a 30% chance of not paying it back, but that might not actually be accurate. Like, your model could have some biases in it, could be unfair for whatever reason. So what you tend to do to improve your policy over time is each time you make your like a new like round of lending, you'll take all the people or whatever that meet your policy, and then you take a couple random people, and you'll just throw them in there to see how they do. You see how they perform, and based off how they perform, you'll now update your policy. Maybe you originally said people from X neighborhood don't receive loans, like like redlining in the States, like they used to do that. Yeah. Okay, like. Is that like something everyone's familiar with?
No.
No,
Okay.
unfortunately.
So in the US, they used to like for like loans and renting and stuff like that, they would like have entire neighborhoods that would just be like just sectioned off, and you just say don't like loan or rent to people in those areas. Those areas were like where the black people lived, like pretty much exclusively. So that was obviously not a good policy.
Hunter, put that on the YouTube.
So yeah, jeez, get canceled. So that was obviously not a good policy.
Yeah.
Because it's just obviously like not true. So what you're saying here to improve your policy over time is you'll take everybody that was in your good books kind of thing, but then you'll also like maybe you grab this guy as well and you just see how he does. And based off how he does, let's say he pays back the loan and he came from this area that you used to say like, oh no, we never loan to people from that area. Well, now you've seen like, well, this guy paid it back. So maybe you update your policy and you say, okay, if they have good income and they're from that area, we'll let them in. And then from that, you'll get like a couple more people from that area. Oh, look at that, they all paid back again. We're gonna lower the income threshold or something for them. And that's how your policy evolves over time, by randomly selecting people who wouldn't have made your policy initially. Yeah.
Do you have to look at like your utility trade-off there then? 'Cause
Yeah,
if
yeah,
you
you-
don't pay off, do we do that?
Like it's like implied, I guess, that it's based off like, because when you're measuring whether or not you do something, it's based off the likelihood and the utility based off the different outcomes. Yeah, and yeah, basically you want to do this because the most important thing is to just gain new information, because you're assuming that your initial information you have in your model is incomplete. And the reason why you would do this is because the only other option is just to accept everybody, and then you'll probably lose a lot of money. And
Is there only one
yeah.
policy per like model, I guess, or can there be multiple policies?
Good question. I don't know. He only really shows one policy at a time.
Bring it up on the exam.
Yeah. Yeah. So that was kind of like, that was like the main overview. Should definitely go deeper in that one because she goes a little bit deeper, but I just can't do it off the dome.
Which chapter is that?
5. Yeah.
So what is this policy and?
Yeah, it's just
utility?
policy and utility. It's basically, she wants to separate the idea of predictions from decisions. Because predictions are just the likelihood of something happening, and decisions are given these likelihoods and what they mean to me. What am I actually going to do? So the last section is causal models and counterfactuals, and this, chapter 6. This section blows.
Oh god.
It's the most difficult section by far, and it's going to be hard for me to teach. Like even my thing at my notes, I say main idea of what actually causes what, and that's it. So, yeah. So for causal, so the first thing that you have to think about is discrimination is often a result of causal models or of causal relationships.
Is this 6 now?
Yeah. And so a causal model is just kind of the idea of saying what actually causes what. So if I have these 3 variables, this is speeding tickets, this is having a red car, and this is tendency for risk, I guess. You may, depending on how you view this, you may say like, oh, if you have like higher risk will lead to speeding tickets. And you may also see that higher like risk or like, you know, like that kind of like personality, you're more likely to buy a red car. The idea behind causal models is you're trying to make sure you don't end up by like saying like red cars lead to speeding tickets. Like you're just trying to actually get a sense of what actually causes what. And there's 3 different kind of forms of these causal graphs. And the causal graphs, the arrows are just saying like A causes B. Wherever the arrow goes is what causes what. So there's kind of like 3 main structures of nodes. And then the last one is what?
These are the causal models.
Yeah. Yeah, so these are causal models. Arrows tell you what variable influences what. So this form here would be what is known as like confounding like kind of setup, because like I mentioned earlier, you may end up proving like seeing some relationship that doesn't actually exist. So if this is exercise, like so here, and I'm going to write it the mathematical way that these are usually represented as well, because that's what she's going to put on the exam probably. So we have variable A is whether or not you exercise, and that is defined as a Bernoulli variable with a distribution of 1/2. Who doesn't know what a Bernoulli variable is? There we go. Okay. Bernoulli variables are, they look like it'll be like A is like a Bernoulli variable of U1/2. And so a Bernoulli variable will either have a value of 1 or 0. So basically this is P. So the value will be 1 at like P% of the time. And the value will be 0 at 1 minus P% of the time. So the expected value of A would then be equal to P. So that would be like a coin flip. A coin flip is a Bernoulli variable with a value of 1/2, a p-value of 1/2. Okay. Does that make sense, everyone?
Yeah, that's
Nice.
a good explanation.
So if we have that like a person is 50% likely to exercise, and then B here, this is whether or not a person is overweight. So if A is equal to 1, if a person exercises, they're not overweight. Otherwise, there's a 50% chance that they're overweight. And we have that if a person exercises, they will not have heart disease. Otherwise, there's a 50% chance that they have heart disease.
Yeah.
Like that would be an example model that you would do. Like obviously not real life, this is just a model.
So the colon equals just like what comes from where?
It's like, I think it's like defined as or set to, something like that.
And so what's the 1, 0 again?
A is equal to 1, then it's 0. Sorry, it's not a very nice way of writing it. I just can't read it
So
exactly.
for C, so C is the heart, so heart disease.
I'm gonna change these. So this is exercise, weight, heart disease. Okay. So what you might see from this data is so the way you have to do this is, does everyone remember joint probability like tables? Laura, could you just bring me the table so I don't have to think about it?
Almost there, bro. Yeah. I don't think these are gonna upload it before the fucking exam. All the slides are
Dude, I haven't checked them.
Just the percentages.
no PDFs.
Is there a time limit on this exam? Or is it all 3 hours?
It's 2 hours.
40 balls.
Hey Mitchell, can you send me your review notes, bro? I saw someone had good shit. Alex, do you have good notes from this review? I don't ask Ben. I'll not that guy.
You want my notes, bro?
Ben, can you send me your review notes
I
from
want
this review session?
I'll send you different one.
Pardon me?
Oh, it's from the
I got a
slides.
good amount.
But you're gonna get like a huge PDF.
I'll just, I'll let you find that.
That's probably better than whatever
It's
these guys
from
have.
the.
What about this, bro?
Yeah, I was looking, I was like, that doesn't make
Yours
sense.
does?
No, yeah, they are.
That's the one.
I am recording. Yeah.
You are? You tired of it?
Yeah, I'm gonna post it. I'll send it to you guys. Pardon me? No.
Will this video have ads on it?
Yeah, I'll be profiting.
You're monetized?
Yeah.
No, you're not.
This is a social experiment.
Can I get Elijah to teach me this entire course one day for $500?
Okay. So, this is what you'll have to do on the midterm, like almost 100%.
Seriously?
Chill. How do you know that?
It's in the practice problem, so I think it's pretty good.
So are these just like all the possible outcomes? of what
Yes.
could happen?
Yeah. So if we look at some of the examples, so you get what the probability of this configuration of variables is.
This is actually huge.
So for example here, we have a person exercised, a person is overweight, and a person has heart disease. The probability of that is 0, because based on our model here, if a person exercises, these will be A's, right? If a person exercises, they won't be overweight or have heart disease based off our model. So basically anywhere here where we see a 1 and then another 1, 0% chance of that happening.
Yeah.
If a person did exercise, and remember there's a 50% chance that a person exercises, then they automatically do not have heart disease or not overweight. So that has a 50% chance of happening, right? These ones, similar kind of thing. Person doesn't exercise, that's a 50% chance multiplied by the oh yeah, these are thirds in when she does it, yeah. Then multiplied by the 1/3 chance that they are overweight, multiplied by 2/3 chance that they don't have heart disease, gives you 1/9. So you just go through and make that entire table, right?
So every possible combination.
Yes.
Oh my.
I'm sorry, how do you get the probability?
You're just multiplying across the conditional probability of things, right? Just take one and try to which one do you want me to say?
The first one.
The first.
Top one. Oh, okay. So what's the odds that a person does not exercise?
50%.
Yeah, 1/2. What is the odds that a person is not overweight?
1/3.
No, 2/3.
Thank you. 2/3. What is the odds that a person doesn't have heart disease?
2/3.
Yeah, that's all it is. So you multiply that together, 4 on the top, 18 on the bottom, 4/18, 2/9.
And those 2/3 are given the fact that E is 0, right?
Yes, yeah, because in this, you'll be, I've written this shittily, but what it would actually say is weight is defined as if exercise equals to 1, then 0, otherwise Bernoulli variable P of
Right.
third.
Are we gonna be given those Bernoullis?
Yes, yeah, you'll be given like this.
Oh.
And then you'll be given the type of graph.
Yeah, you'll be given this, and you might be given something that says
You'll probably be asked to draw it though.
E goes to W, E goes to H. You might be given some, like, you could be given just this.
And so we construct that chart, or
Yeah. And technically you don't even need this, but I should probably get this.
Can you explain the notation of W and H again?
Yeah.
Yeah, it's written better in the slides. I was just being lazy. It would actually be written like something closer to like W is defined as
I get this part. It's more like math.
E is equal to 1, then 0 else.
What's what?
What's separation?
I'll have to repeat
Right?
the note.
So if E is equal to 0 in this case, then the probability of W is 1/3.
Yes.
Okay.
Yes, it will have a 1/3 chance of being 1, 2/3 chance of being 0.
Yeah.
This makes sense.
Yeah.
So the platform, the question was just to make the table, is that what it was?
No.
What was the question?
Yeah, so what we're getting at is the question now is, if you just had this table, for example, does being overweight cause heart disease? That would be the question from this, because what you might see in this kind of thing is you might see that, like, since it's basically saying people who don't exercise are more likely to be overweight and have heart disease. However, if you're looking at that data, you might look and be like, oh, people who are overweight have heart disease. But our model actually says that it's because people who don't exercise are likely to have heart disease and be overweight. So that's the area issue you have with confounders, is you might believe there's some third connection here that doesn't actually exist. Another example could be, so kids are at parties. Kids who are at parties eat candy. Kids who are at parties run around a lot because they're excited they're at a party. You might look at that data and say, kids who eat candies run around a lot. But really, the thing that's causing both of them is being at the party.
Is it the direct and indirect?
No, that is this one. Let's look at that one. So the way that you determine whether or not this is true is you do what's called a do operator. So a do operator essentially sets some variable equal to some value, and that breaks one of the links. So I'm going to change these so they match up. So what you will do is you will do a do operator. So you might say do W equal to 1. So what this is saying is we are setting in our table that, or setting in our mind or whatever, that the person is overweight. Like that's kind of what you're doing. So since we've done that, what that does to our causal graph is it removes all the links into the variable. And the reason why that's important for analysis is if this link actually does exist, if you remove this and you are just left with this, you'll be able to find out whether or not there's a connection. In this case, since there is no connection, what we'll find is comparing the conditional probability of having heart disease given being overweight is the same as the probability of or something is like the same as the probability of do W equals 1. Oh no, I'm combining two examples, and that's why I was getting confused. Yeah. Let me stop there. Let me center myself. Okay. Basically, what you're going to see is instead of it shouldn't be equal. They'll be different because there is no correlation between the two. Oh no, I'm blanking on how you do this. Okay. So yeah, the way she does it, she doesn't use the table explicitly for this one, I don't think, but you do need to use the table. She does it both ways. I don't know. Basically, the easier way to look at this one is if we say do W equals 1. Does our value here change? Because now we've said W is equal to 1. Does H change? No. So from that, you can confirm that weight does not influence heart disease. However, there is some other way of doing it where you sum some of these columns and then you take probability of, it's like W and H, and then you divide it by the probability of W, and that will also tell you.
Is this all on the slides?
Yeah.
Okay.
Yeah, I would just look at the example for heart disease and look at the example for, the better example is the one in her posted, solve problems. I think it's problem 7.
Yeah.
She goes through the actual math of it. I'm just blanking right now. But essentially, you're trying to compare like things by setting certain things. It's called substitution as well. It's either a do operator or substitution. And by setting variables to a certain thing, you can tell whether or not a thing is actually causally related.
And so this would get like more complex with like one like the far right one where there's an indirect.
Yeah, like they can.
And
Yeah,
it just could it get like real weird or?
yeah, well, even like you can get weird results even from this. So like this one right here, right? This is a confounder, and the reason why is because E would be like a confounding variable on H. You think there's a link here, but E is the confounder. What you can also have is this is called a collider, where you have two things leading into the same place. And with that, you can, depending on statistical distributions, you can make like conclusions that are just clearly false. So for this one, it would be if you were to say that like toys make kids happy, so this is toys, and candy makes kids happy. Well, I'm sorry, goes into happiness. So basically, kids who have toys are happy, kids who have candy are happy. Depending on the varying levels of happiness and depending on like the size of the samples and stuff like that, there is a way that you can statistically show kids who have candy are like unhappy. Like, I don't fully get that part, to be honest. But like she also gave an example, like the same thing for disease. This is disease 1, risk of being hospitalized, disease 2. Because you can show using this math that somehow having disease 2 makes you less likely to be hospitalized because of something with how this setup goes. I don't really know.
So just shows like which one, like it's kind of like with sorry, I'm blanking now. Earlier we were talking about
it's something to do, I think, with like having a path through
scale.
here.
What is it called? Shapley? Is it kind of like that? Shapley, where you can see which one is like stronger, like which makes things more happy, or is that not really what we're doing?
I don't know if that's really honestly. I think it is something to do with inferring there's a link between these two when there doesn't actually exist.
Okay.
Because if you're trying to like say like disease 1 is correlated with disease 2 and then both of those correlate to hospitalization, you could get like a reverse correlation, I think. Just know that colliders can cause issues. And that's the form of a collider.
The opposite.
Yeah.
And then the last one,
Confounder, collider.
this is like a mediator setup.
Mediator.
So here C is the mediator. We have the direct link between B and A. So B could be gender. A is admitted. And C is program choice. So this is the example from UC Berkeley, I think it is, where they showed if you just look at the total number of people admitted, they saw like 60% of men are admitted, and like 40% of women are admitted or something. I don't know the actual numbers. But then they were looking at that and they were like, oh shit, we're discriminating against women. But then when they actually looked on a per program basis, so program's the mediator, women were actually accepted more frequently than men. Women were just applying more to more difficult programs. So what goes on there is basically this is kind of like this kind of situation they had there where gender certainly did influence admissions just because there are like differences between them and like it's like more complicated. Like I'm sure this branches off in 100 ways in actual real life. But since women were more likely to choose difficult programs, they were less likely to be admitted through this mediator. And it's just something, like she doesn't say whether really it's like good or bad, but it's just like kind of something to be aware of that you can get weird results because of the mediator that's going in between. And an example she gave also was like, and this is actually one of the questions she gave, is kind of like, first she asked which of these is the direct link and which is the indirect, so clearly direct link, indirect link, right? But then she asks if you were to remove either the indirect link or the direct link, what would kind of like the implications be? So if you were to remove this direct link, if gender highly influences what like level of education you get, then that could mean that it's basically like you're still in the same place. If gender is like really, really good at influencing what education you get, then it might be harder to get like a job just based off of gender. Or if gender and education are kind of like weakly correlated, you might end up in a thing where it's more fair to not know the gender directly because you can't directly discriminate if that's like your main concern. The hiring manager is directly discriminating. Alternatively, if there isn't a good correlation between gender and education, and now you only give them the gender, they might just like, and they don't really know, they might be admitting people who are like not qualified for the job. So yeah, that was kind of just showing like the implications of the different effects of mediators, whether they're like strongly correlated or weakly correlated. And yeah, so the main idea with all of these, and especially like the do substitution stuff, is they are true of averages. So over the entire like population of everything, like it's true. If it's saying that if you set like weight equal to 1 and it says it's not correlated, that's like true of everybody. But the second idea of counterfactuals, and this one's really weird, is counterfactuals are basically asking for an individual, if something was different about them in a hypothetical world of an event that had already happened, would the outcome have been different? So with those, like an example could be like, and this was an example I saw in like some paper where I was trying to like understand it, was saying, it was a person's whole like PhD thing, was they were saying, would I have gotten my PhD if I had shaved my beard? And technically, using counterfactuals, there is some way to calculate that, because you know what's already happened. You know that he's graduated already. However, given the information that he had a beard when he graduated, and given the information about everybody else that you know, you can calculate the probability that he wouldn't have graduated if he had shaved his beard, and like his conclusion is it's a very, very small percentage, like it barely changes what happens. But a more real example would be, you've got a setup where you know the weather is a Bernoulli variable. I'm gonna make this better. The weather is a Bernoulli variable, 50% chance of occurring, and then you have like road 1 and road 2, which each have, if like it's bad weather, they have bad traffic. I'm not gonna write that, just please remember. And then otherwise, there's a 50% chance that they just have traffic if the weather is good. The question would be, if I am on route 1 and I have like bad traffic, what is the probability that if I had gone on route 2 today, I would have not run into the traffic? And to get that number is really hard. So,
And not the exam.
what?
And you won't be in the exams.
Probably not. If you guys don't want to go over it, I don't want to go over it, so.
I think Gavin wants to go.
It's not true.
Okay, because I don't know if I can get it off the top of my head. Like,
We can skip it.
yeah, because you need like, first you get like the probability of X, then you use Bayes' theorem to get probability of X given Y. Like it gets bad, like, because that's equal like probability of Y given X, and then that's the probability of X or something like that.
I thought this was gonna be
And
a
then you
bird
do one
course,
minus
bro.
the other one, and then you have to take 2 cases and do conditional probability on them. Like, it gets kind of messy.
What is Bayes optimal again? That might be different from Bayes theory.
Yeah, that's different. Yeah, Bayes' theorem is basically just saying, oh yeah, it's probability of Y given X multiplied by probability Y, I think. So it's like saying like you can get the probability of X given Y if you have probability of Y given X multiplied by probability of Y divided by probability of X. I think that's Bayes' theorem.
And what's Bayes optimal?
Mitch, don't ask that.
Yeah, but basically the main takeaway, the thing that's actually important for you guys, I think, is when you're doing substitutions, you're learning something about the entire population if it was different. So an example would be if you were trying to tell how tired people are when they're like didn't eat breakfast, you would use the do operator to set like eating breakfast equal to 0, and then see on average how has that affected every single person. On average, how hungry are people? For counterfactuals, it would be, man, I was tired today. Would I have felt tired if I had eaten breakfast this morning?
Okay.
So that's like the main idea. So counterfactuals are for individual events that have happened in the past, and substitutions are for figuring out if something else was different about the entire world, what would have happened.
Gotcha.
Yeah, and that's it. That's everything.
Awesome. Thanks, bro.